will share you all, Andrew.
Okay, thank you very much.
Andrew was already introduced by Kalina, so the word is with you.
Thank you very much. So, when we finished on Monday, which I appreciate, this is by the way, thank you for coming. Last day, 3 weeks, I lost a small bet with myself. I bet you'd all be at home in bed nursing hangovers. So, thank you very much for coming in at an ungodly hour. When we finished on Monday, we were looking at the possibility of building a photonic quantum processor. And the idea is that you would have some set of single and entangled photon sources synchronized in time, very well characterized. You would bring them into some kind of reconfigurable circuitry. This will be a photonic chip. There'd be some kind of quantum memory and delay process, and then you detect the outputs. And in everything we did up until that point, we talked about how the power of quantum computing in general comes from entanglement. These apparently nonsensical correlations between quantum systems that have cost and a benefit. Cost is to describe a quantum system as soon as entanglement is a possibility. You need an exponential number of equations or an exponential number of pieces of information to describe the system. So a 2-qubit system you can describe with 16 pieces of information. A 4-qubit system requires 64 and so on. The next thing, we also then, did we go through simulating quantum systems? We did, didn't we? Something. Okay, well let's... Why not? If no one remembers it, I'll assume we did. So Richard Feynman in 1982 pointed out this was a real problem. The fact that as physicists or chemists, if you wanted to describe even a very simple, interesting system, for example, lithium. Okay? This is a very tiny atom. Hydrogen, helium, lithium. We cannot do a full description, a full configuration interaction, full grid model of lithium without making approximations. There's a PRL from 2005 where they're talking about how you do quantum chemistry calculations, and it finishes with lithium is impossible to model for the foreseeable future. Now that's not right. That's a very, very simple atom. There's a lot of lithium in the universe, and so it's strangely depressing that we can't model it. Feynman said this means we're doing something wrong, because nature handles these very simple quantum systems and more complicated ones straightforward. If we're having a problem with it, we're approaching it from the wrong direction. And he suggested perhaps it would be better to use a quantum system as your computational building block. So you would simulate or emulate or model quantum systems using quantum systems. That's a lovely paper. It's well worth a read. No one really did anything with that insight for 14 years. Until the mid-90s, when a scientist from MIT called Seth Lloyd said, yes, Feynman was right. It turns out that if you take a set of qubits, 2-level quantum systems, as we discussed on Monday, send them through a quantum computational circuit, you can, to arbitrary accuracy, simulate any evolution of a quantum system. Some people have turned that around and now argue that if you can't, I did do this on Monday, if you can't simulate a quantum system this way, then it's not physical. That was a lovely proof of principle paper, very mathematical, but what it didn't give you is a mechanism where you could take a quantum system of interest, say a quantum chemistry problem, turn the handle and see how to build a quantum computer to model that problem. That came out in a paper in 2005 in Science, and the physics behind that paper was you take the eigenvalue problem that you have in quantum mechanics and turn it into a phase estimation problem. And I guess if there's any take-home message about quantum computers, is all they are in any physical system is an interferometer. They're a way of manipulating phase and estimating phase, measuring phase. So nearly, in fact, all of the quantum algorithms that I'm aware of end up mapping back onto phase problems. So once you map it onto a phase problem, it's game over. And you can also do chemical reactions that way. So I did discuss this on Monday. All of quantum chemistry, apart from the very hot and the very fast, you can map as being a problem in potential energy surfaces. The traditional approach to calculating those surfaces in current computational quantum chemistry using classical computers is you represent the system, you find an algorithm called the full configuration algorithm that is exact, but unfortunately it blows up exponentially, and then you start making approximations at different points, depending on the chemical system that you're trying to model. And you get this wonderful branching structure of approximations. And the kind of dotted lines are, well, you can kind of see this might model over to here. And people spend their careers coming up with better approximations to do interesting systems. So the promise of quantum simulations is that you might be able to take the wave function and Hamiltonian of the quantum chemistry system of interest and just solve it exactly with a quantum computer. This polynomial scaling, if you're a computer scientist, if something blows up exponentially, it doesn't scale. Because every time you add one more instance to the problem, for example, one more molecule, or one more atom to a molecule, the problem blows up exponentially. So for a computer scientist, if it scales polynomial, it's game over, you can go home, yes, that's efficient. For experimentalists, the problem is some of those polynomials are huge. Right? If it's a d to the 20th polynomial, that's not still terribly attractive. But it turns out that polynomials for chemistry aren't too bad. The full configuration interaction scales as the fifth power. It's been shown that you can model chemical dynamics just as a square, the number of particles, and you can calculate molecular properties, in particular things like the dipole moment, with a single query of a quantum computer, regardless of how many atoms there are in the molecule. And in protein folding, there's been a lot of work working towards showing that this is solvable by quantum computation. And then on the archive last Thursday, there was a paper from a group in Singapore showing that the ground state of DNA in the particular way that it's coiled is in fact due to continuous variable entanglement. Now, it's early days to see if that's a very deep insight or not, but it is suggestive. Of course, you could argue the fact that molecular hydrogen exists is due to entanglement, so we haven't learnt anything. But they're suggesting that the particular superstructure shape exists because of entanglement. If you wanted to describe hydrogen, the easiest way is take two hydrogen atoms, form molecular orbitals where atoms A and B are combined as follows for the S states, model a ground and excited state. There's 6 basis states that you can describe. A couple are forbidden because of the Pauli exclusion principle. And then you end up with a 6x6 Hamiltonian. And you'll notice there's a block structure. There's a red 2x2 block, a black 2x2 block, a blue 2x2 block. And this, of course, was extremely well known to Dirac. Here's a picture of him in front of a blackboard solving for hydrogen. What he wouldn't have known is that, of course, you can take these Hamiltonians, turn them into the unitary evolution of some quantum system, and then estimate the phase. I won't go through all this again, we did this on Monday. The important part is that you end up with an entangling gate. Yeah, we did do this on Monday, so I'm going to skip ahead. To future prospects. So that's kind of state of the art in simulations of quantum chemistry today. It's not only quantum chemistry that people are starting to do quantum simulations. In the last 2 months, there's been papers in Nature and Science on simulating relativistic motion of ions, on simulating annealing in solid state systems. These are all toy instances. There is a paper about to come out where people have built a physical system where they have simulated a problem that they cannot solve with a classical computer today, and that was with a handful of ions, an 8-qubit problem. So we're very rapidly approaching the point where we're getting beyond what we can do if you take every computer on the planet. So, will it affect what you guys are doing as physicists in the next 2 years? Probably. But on the timescale of 10 years and 20 years, definitely. This is the new tool for modelling quantum systems. Discussed that last time. Right. So up until now, I've been saying the power of quantum computing comes from entanglement, and that was commonly believed to be the case. Now I'm going to try and convince you that that's not always true. This is quite a commonly held belief. There's a lovely article by Scott Aronson in the MIT Technology Review. Entanglement is a quantum form of correlation between two more qubits. All parties agree that it is a non-negotiable requirement for quantum computing. So if you don't have any entanglement, you don't have a quantum computer. Entanglement is the resource at the core of all quantum information science from the last Solvay conference. It is known that if you have pure states, so this is states with no disorder, you require entanglement. That's been proven mathematically. And it's also been shown that an arbitrarily small amount of entanglement isn't enough. You need a certain level of entanglement that scales appropriately with the size of the problem. So you need a certain amount of entangling power in any system you build. It turns out you can have too much entanglement. That's another issue. But there are no such proofs once you allow mixed states. And you come to a feature, if you will, of modern quantum theory, quantum information theory, experiments versus theory. The experimentalists, we all know that pure states are a collective delusion of theorists, right? No experimentalist has ever measured a pure state. We get things that are almost pure, but they're not pure. Nearly all theorists love modelling pure states because the maths is easy. Once you go to mixed states, it's a lot harder. And there is a gap between those two worldviews, and this kind of creeps in that gap. So, if you have entanglement, is that enough to build a quantum computer? And the answer is no. So the question you can ask is, if I've got a number of pure systems and I've got entanglement, what's the least little step I need to do to build a quantum computer? I'm an experimentalist, I'm lazy, I'd like to know the least work that's required. So it turns out there's something called, the jargon's horrible, a Clifford gate set. It's a controlled NOT gate. This is a 2-qubit entangling gate. And a couple of single qubit gates, something called the Hadamard and something called an S gate. The S gate's just a phase shift, and the Hadamard is a gate that takes a logical 0 and turns it into a superposition of 0 plus 1. Are there any optics people in the room? Okay, a couple. So in optics, this is a polarizing waveplate. These are very simple gates. There's also a different kind of phase shift gate called a T-gate, just a different kind of phase shift as the qubit goes through. It just changes the phase between the logical and 0 and 1. Both of those on their own, you can efficiently simulate with a classical computer, but when you add them together, you get a universal quantum computer. It's quite odd. You've got two things that are both very simple to describe on their own, but when you add them together, the interactions between them suddenly become far more powerful than you would credit. Well, what else is like that? I said on Monday, there's this 3-bit or qubit gate called a Toffoli, that in fact you can show all of classical computing can be done just with Toffoli gates. And that means, of course, that it's classically simulatable. If you add to a Toffoli a Hadamard, which is just this simple superposition, again classically simulatable, the combination of those two things gives you a universal quantum computer. Alright, well, what else can we do? Well, there's a gate called the Valiant gate. It's a 2-qubit gate. I'll come back to exactly what it does in a minute. It's classically simulatable. And if you add to it swap, just the act of saying, I have a qubit here and a qubit here, and I move them around. Now that, of course, is obviously easy to simulate with a classical computer. Heck, I'm doing it with my fists here. Right? It's very easy to do. But the combination of swap and this particular kind of entangling gate gives you a universal quantum computer. Now, this has caused a lot of thoughtful what the in the community. They're really not quite sure what this means. But it does seem to suggest that, oh, by the way, a swap gate, of course, although it's easy to physically show that a swap is moving fists around, if you have fixed qubits, that they're, for example, ions buried deep in a solid, to move the information from one qubit to another, you need 3 controlled NOT gates. So the idea that swap is an easy thing to do to physical objects, but a hard thing to do to the information on those objects, gives you a clue what's going on here. But in some sense, swap is much easier than doing phase shifts, at least for mobile qubits. These entangling gates, the controlled NOT is easy because lots and lots of people have done it all over the world with photons, ions, superconducting circuits, atoms. The Toffoli, until 2 years ago, was really hard because it's a 3-bit interaction, and there aren't many natural 3-body interactions that occur with a high probability, so you have to mock them up from 2-body interactions. But that's now been done here at the University of Queensland with photons and with ions at Innsbruck. And the Valiant gate, which is a really funky gate, it's like a controlled NOT gate in the parity space of the qubits. And if I'm just raving now, don't worry about it, just know that it's funky. It hadn't been done, oh, this is an old slide, but it's now also been done in an optical system. So these gates, for example, the Toffoli gate, are used in, there's a whole field of theoretical computer science now where they say, how do I build the best possible quantum computer? And they'll come up with a recipe using 3-qubit gates and 4-qubit gates and funny controlled unitary 2-qubit gates. And even small quantum algorithms require large numbers of controlled unity and Toffoli gates. Here, for example, is something called the multiplexed full adder, which is part of any future Shor's algorithm implementation. This is how the theorists draw it, or the computer scientists draw it. This is how you would realize it with Toffoli gates and controlled NOT gates. You can see 3 and 4-qubit Toffolis there. That itself then gets added into something called a MAD gate. I'm going to make these names up, multiplex gate, and so on. So you can see they're important to be able to do. Now, earlier I said entanglement important. Back in 1998, Manny Canil and Ray LaFlamme said, what happens if I have a computing circuit where all of the qubits are mixed, and by that they're completely decohered, they're completely classical, and I have one pure qubit? What will the answer be? Now, if I was to put a bottle of scotch on the table now and say, bottle of scotch to someone who gives me the right answer, what would the answer be? Come on, have a go. It's a nominal bottle of scotch, but you never know. Anyone? Friday morning. Okay, I'll take the scotch. I would have said, certainly before this paper was published, nothing will happen, right? That's a classical system. If you've got a whole bunch of noise, and you add one, a million noisy qubits, and you add one pure qubit, you've got a million noisy qubits. It's nothing good can happen there. But it turns out I would have been wrong and lost my invisible bottle of scotch. There is a complete set of problems where you can solve them with such a system. They look at first fairly artificial, Pauli decomposition of a unitary matrix, quadratically signed weight enumerators, blah, blah, blah. This one's kind of interesting. You can solve efficiently the Jones polynomial and knot theory. You can do quantum measurement efficiently. And the example I'll walk you through, which is a little toy example, but it kind of underpins all the others, is estimating the normalized trace of a unitary matrix. So if I give you a unitary matrix and I say, what's the normalized trace, that problem blows up exponentially. So if I give you a big enough matrix, MATLAB will grind to a halt and just fall over. You can't do it efficiently. So the way you do it efficiently is you build the following quantum circuit. You take a pure qubit, you send it through a single entangling gate. So this is a gate that would entangle if all the inputs are pure. And into the register for the gate, of n qubits, you send mixed states, noise, just noise. You then throw the noise away and you measure the output of the single pure qubit. Now that looks useless. But it turns out that control output is this state, where the coherence, so this is the amount of logical 0, the amount of logical 1, these are the coherences between them. The coherences depend on the trace of that operation. So if you do an X measurement here, you pull out the real part of the trace. If you do a Y measurement here, you pull out the imaginary part of the trace. Remember, X and Y are just the Pauli operators, so you can just project onto that basis. And after you've run it L times, you now know the trace to an accuracy of 1 on root L. Or put it another way, if you want an accuracy of epsilon, you have to run the circuit 1 on epsilon squared times, and that doesn't increase with the size of the unitary. That just goes quadratically with the number of times you want to run it. What does that tell you? Well, it might tell you that you just haven't done your classical maths well enough. Right? Shor's algorithm doesn't prove that there isn't a standard mathematical approach of efficiently finding the parameters. The existence of this doesn't tell you that there's a better way you can do it classically. But there's reasons to believe that none exists. And the reasons have to do that if it did exist, it has implications for a whole class of complexity theory, how we enumerate complex systems. So here's an experiment we did. We took 2 qubits. These were photons of light. One was purely polarized, one was just unpolarized light. Unpolarized light is really easy to get. Sent it through an entangling gate. As I said, there are no pure qubits, so we made something that was quite close to pure. And we got out, shown in red and blue, the real and imaginary parts of this unitary as we changed the angle theta here in the unitary operation. Okay, that's fine. What happens if the control is mixed? Well, the signal decreases, but you still get the curves. Right? They still look pretty much the same. They're just a little bit smaller. And it turns out that your accuracy now requires further runs by amount alpha squared, where alpha is kind of the degree of your purity. But if you look at that carefully, that means that even as alpha approaches 0, you still get an exponential speed up over the best known classical approach. So that means even if you've got a quantum computer that is perilously close to being completely noise in and noise out, you still get an exponential advantage. Now, what? That's really quite confusing. It shouldn't be that way. So where is the power coming from if I've got a completely disordered system with just a vanishingly small amount of entanglement? So this is where it hints that there's something new to quantum mechanics that we've missed. If there's no entanglement and there's still something powerful going on, maybe we shouldn't be looking for entanglement. So there's no significant entanglement in that algorithm, and that's been proven mathematically. And in our experiment, we measured the tangle was to within error 0 for all settings. So that means the output's always separable. You can beautifully describe it by classical physics. So where's the power coming from? Well, it hints that there are correlations between quantum systems that isn't entanglement, beyond what Schrödinger thought about. And in fact, people, for all quantum computing, entanglement's not necessary. For a lot of it, it is, but not for all of it. So Schrödinger in 1935 said, look, entanglement is the following mathematical definition, and he defined it as, is the system, an answer to the question, is the system separable with respect to some partition? That's a very mathematical definition. It's not a very physical or intuitive definition. Early in the noughties, people came up with a more physicsy type approach, something called the discord, which is if we have a pair of entangled particles, you have an entangled particle and I have one, are the local measurements that I can perform on my entangled particle that would allow me to extract all the information about your entangled particle without altering what you have. If our particles are pure, that just collapses back onto entanglement. But if they're mixed, partially mixed, then that captures something more. And you can measure this quantity, the discord, and yes, you can see it varies. And it turns out that as long as the discord is non-zero, you can have an efficient quantum simulation, even with vanishingly small amounts of entanglement. I'll skip over these suggested points. So I guess the take-home from this little section is the following picture. There is a sea of classical states, and in the middle of it there's this icy mountaintop of Bell states. These are states that violate a Bell inequality. They're quite entangled, they're quite pure. Around there, there's something called the steerable states. This is shown as stony slopes because it's an idea that Schrödinger came up with in 1935, and in the intervening 70, 80 years, there's been one experiment. So it's an idea, but not a lot's been done. Surrounding that, both of these states are a subset of entangled states. There's been a tremendous amount of work done on entangled states. And now it turns out surrounding all of that, there's this beach of separable states that are nevertheless quantum. They have a discord greater than zero. And this is an extremely hard talk to give to people who've been doing quantum for a long while. Because if you've been doing quantum for a long time, you see the word separable states and you think classical physics. What this shows you is there are separable states that are still quantum, that have a quantum advantage, quantum features, and can be used for an exponential advantage in calculations. And together this forms the island, non-classical island, land of quantum computing, here be funding. So if we go back to the earlier statements about entanglement is necessary, they're almost right. You can say entanglement is a quantum form of correlation between two or more qubits. All parties agree that such non-classical correlations are necessary for quantum computing. There is more to quantum correlations than entanglement. And then you change entanglement in the next statement to non-classical correlations and the resource of core quantum information sets. All right, how am I going for time? 20 minutes, good. So let's now talk about fault tolerance. I touched upon this on Monday. This is the idea that our laptops are full of chips that are faulty. And yet, on the whole, with the exception of running anything from Microsoft, the programs work pretty well. So what's going on? What's going on is that there's fault tolerance. You might have a 10-qubit register, and two of the qubits are just there to check and see what the other 8 are doing. Okay? You do parity checks. If something goes wrong, it'll show up, and you throw that away and repeat the calculation. Well, you'd like to do that with a quantum computer, but there's a couple of problems. And the first problem is you can very easily, for a classical computer, figure out how well you need to do that to get a certain level of performance. If I want 99.99% accuracy in my calculations, I need this level of error there. That's really hard to do with quantum computers because the thresholds you calculate are based on the idea of a certain amount of error per gate. And a gate is a 2 or 3 qubit thing sitting in a small Hilbert space. And when you take normal logic gates, just say I can describe a normal logic gate by 3 pieces of information. If I have n of them, I can describe them by 3 times n pieces of information. So if I understand what error I need for that one gate, I can just multiply it up. Whereas that's classical. For quantum, it blows up exponentially. So even if I understand what's going on a per gate basis, I may not understand how the errors will propagate into this exponentially growing system as I add more qubits. So I have to make assumptions. And there's 2 classes, there's 2 approaches that people have used. There's the optimistic approach, that the errors will be simple, that they'll be independent of one another. This leads to quite high thresholds, and you can solve these problems numerically. And then there's the pessimistic approach. And when I say there's a complex error, you assume that I have some quantum computer. My error is going to be an adversarial quantum computer doing the worst possible thing to my calculation across every qubit, themselves using entanglement at every stage of the calculation. So that's deeply pessimistic. It leads obviously to lower thresholds, and it's extremely hard to solve what's going on. But people have done that. And so here's, for example, a cartoon of a quantum circuit. The yellow boxes are 2-qubit entanglement gates, the blue and green boxes are single-qubit gates. And you assume that a gremlin comes in at the points where the little stars are and adds some unwanted process with some probability. Okay? You're not adding necessarily just noise, you're adding a process. You could be taking a pure system and rotating it to the wrong basis, or you could be taking a pure system and decohering it, or you could be taking a slightly decohered system and making it pure partially with measurement. There's some process. That cartoon, by the way, is from the first use of gremlins, which was a book in 1947. Anyway. In large circuits, you're really unlikely that all those errors are going to add in the worst possible way, because for that to happen would require entanglement and quantum coherence, which is hard. That's what we're trying to do in the first place. But depending on the kind of assumptions you make, you could find that, look, thresholds of 3 to 6% is fine. If you've got errors at 5%, you can still build a scalable quantum computer. If you assume the worst case, then you're going to need 20 parts in a million accuracy. That's quite hard. The other problem is we don't actually know how to move from those thresholds that are calculated on the basis of some theoretical things and tie them to what we do in the lab. So for example, for an ideal control Z gate, this is related to the control NOT gate, you can rotate it into a basis where that big blue spike represents do the ideal gate on the control and target qubits. And all the other elements along the diagonal represent do the ideal gate and then afterwards do a noise process. For example, do nothing to the control and a sigma x rotation to the target, all the way through to do the ideal gate and then do sigma z's on the control and target. Those elements as highlighted are the error probabilities for the gate. The height of that first element is something called the process fidelity, and you can measure that with a so-called witness. It's a smaller set of measurements than doing the full tomography. It turns out the gate error is bounded by the identity of that witness, and if these errors have no coherences with this element, so in other words, if all these things here were flat, which you can see they're not, then that would exactly give you the error per gate. What happens in the lab? Well, as I said on Monday, we have a high energy beam of photons. It goes through a nonlinear crystal, and occasionally, one time in a million, one of these photons splits into a pair of lower energy photons. We use that as our single photon source. We send it through our entangling gate. And you might get some kind of average gate fidelity like that, around about 90%. Well, I had a very sharp German student a few years ago, and I said it would be kind of nice if we could know when each of these photons were coming in. So we set up an experiment where we sent a laser beam back and forth. So we've got a pair of photons here, and then as this beam comes back, a pair of photons there. And in each case, we triggered this photon, so we knew where in time this photon was coming and where in time this photon was coming. And we set it up, we had a beautiful system so that all you had to do was swap a pair of fibers around, just interconnects. Right? This is very nice. A supervisor could do it. Send them into the gate, and immediately the gate fidelity dropped by about 7.5%. So I said to the student, oh, we must have stuffed up, meaning you must have stuffed up, how we did the source, go back and do it again. And he was German, so he did. And then he came back and he said, no, I did it right, you're wrong, which was good. And it turns out, in that situation, the mode matching was exactly the same. All the optics was right, we had all the fibers right. The only thing that was different was how we were running this source. And in particular, let's see how we can get into this. Oops. There's a possibility when you're running this source now that, yes, you might get a pair of photons like this and like that. But with a very similar probability, you might get two pair of photons here and no photons there. Or two pairs of photons here and no photons there. And because then those two photons that are coming in here can split through the gate and each come into a single output, you count that as a successful calculation, even though it's just nonsense. So we did a model on that, and it turns out that this case where you get two photons in this input instead of one photon, because a tiny amount of time, less than 1% of the time, but because these gates are non-deterministic, they don't always work, that gets amplified up by orders of magnitude, and when you look at how much error it adds on the order of, it adds on the order of 16% error. There's also some error due to the fact that these beam splitters aren't perfect. That's about 3% error. And then you can explain this is the ideal process matrix for such a gate. This is the model process matrix, and this is the experimental process matrix. And if we zoom in and look how well they overlap, the ideal and the experiment overlap by about 82%. The model and experiment overlap by about 85%, and the agreement between our model and experiment is 98%. So we know pretty well what's going on, and these higher order terms are a problem. This text, joy, that is Microsoft. So the errors are about 16% due to these extra little photon terms creeping in. So if our colleagues who are working on quantum dots tomorrow came up with a key turn photon source, and some of them are very close to doing that, and we get it off of them, the error in this gate then is dominated by the mode mismatch, and that's about a 3% error. And that's under Knill's tolerance threshold. So if you could, in this particular quantum computing architecture, if you could solve the problem of single photon sources, you're into a scalable regime. Now, whether that will happen in a timely fashion is an entirely different matter. How do you count photons? Okay? It turns out, if we got you into a sufficiently dark room, you all can count photons, at least green ones, with your eye. Somewhere, your resolution, depending on your age and genetic background, some of you can count down to 10 photons, 7 photons, and some of you can count down to the single photon level. So it might be very tempting to just get a bunch of cheap students, put them in a room and count photons, but it's not very easy to calibrate. So typically people use the following methods. We'll use something called a single photon counting module. Now this is just a normal PIN photodiode running Geiger mode. Think of it as an internal photoelectric effect. When a photon comes in, it takes something out of the conduction band and promotes it to the valence band within the semiconductor, and it knocks on a whole lot of things. They have several advantages. They're cheap as chips as far as experimental things go. They're about $5,000 each. That's cheap compared to what I'm about to show you. The quantum efficiency is okay, about 2/3. They don't count false photons. So if you run them in a dark room, completely dark, or shove your hand over the front of them, you get a dark noise rate of about 50 counts a second. 1 megahertz count rate. They tend to blow up. So if I take the amount of light that is in this room and shine it on one of those detectors, there's going to be more than 1 million photons a second. Smoke comes out of the detector. As you know, modern electronics is based on smoke. When you let the smoke out, it doesn't work anymore, and they don't work. So you have to be very careful with these. But they do work at room temperature. They have a Peltier control that takes them down to about -35 to improve the efficiency. There's another kind of detector called a visible light photon counter. This works on impact ionization of arsenic and silicon. Quantum efficiency is quite high, at 95%. They have high dark noise, a bit of a problem. You can run them at 6 degrees Kelvin, and there's currently something like at least 20,000 of them sitting in Fermilab in Illinois. These are the detectors that are used in the large detector arrays. So if you order them by the 100,000, they're quite cheap, but if you're ordering them for a lab to say you want 16, the company that makes them wants to charge you $400,000, and in fact they send you a note saying how delighted they are to offer their first contract under $1 million, and you should be pleased that it's very cheap. So they're not really an option. This brings us to the kind of current options and something called a superconducting bolometer. Now, a bolometer is something that measures heat. There's a couple of ways you can do it. One is you can take a metal wire, meander, as shown. And then what happens is when a single photon comes in, if it gets absorbed by the wire, it heats the wire up. You get a hot spot that suppresses the superconductivity. The electrons then have to flow around that hot spot, and as they do, the electron density goes above the critical amount, and the whole thing ceases to be superconducting across the width of the wire. You get a resistant region, and that gives you a spike. That tells you, yes, I have a single photon. These are fast, but their disadvantage is, if you look at that, how much of that square is covered in light blue? Less than half? It's just a grunt to show you a weight would be really appreciated. There we go, I've got a thumbs up even better. And in fact, a tiny amount. These things only have efficiencies of 5 or 10% because that's kind of the filling factor of these squared. So if you want high efficiency, you go to a different approach. You have some thermometer where light comes in, is absorbed. There's a weak thermal link between the superconducting region and the thermal sink. This light grey area in the middle here is one that we have sitting in our lab downstairs. And when that comes in, the whole thing ceases to be superconducting and you get an increase in resistance. This is an old slide. The quantum efficiency of just the reflected metal is about 20%. The first AR coatings took it up to 80%, and they're now at 98.5%, 99% efficiency. So that's good. There's 0 dark counts. That's good. So it turns out with detectors, you can have any two of the three following things. You can have speed, you can have efficiency, you can have photon number resolution. The ability to tell the difference between 1 photon, 2 photons, 3 photons. Both of these detectors have photon number resolution. This one is fast, which means it doesn't have efficiency. This one has efficiency, which means it's not fast. So that's the kind of space. If you're going to make a bolometer, as I said, you can make it efficient. Oops. You can make it efficient by putting anti-reflection coatings on. But that works at a fairly narrow range of wavelengths. What if you wanted to make a bolometer that was efficient over a broad range of frequencies? You might want to do this because you're doing quantum computing. 5 minutes, great. And you have very broad photons in the quantum computing. You might want to do this because you've got something, say, or I don't know, sitting in the front of a missile, scanning for jamming frequencies, and you want it to work at all possible frequencies. So you'd like a broadband coating, and you'd like it to be black. Basically, you're looking at it, you don't want to see any light coming back off, because if you see light coming back off, it means it's being reflected. You'd like it to be efficient. You want the photons to get turned into phonons. You want it to not have to scrape it off after a little while and reapply it. You don't want it to short out the detector, and you want it to be thin, because if it's thick, the phonons will take too long to get to the bolometer, and it will slow down the speed. One approach that people are trying for this, in fact we're trying it here, is to use something called melanin. Melanin is the stuff that makes your hair black or brown. If it's black, it's eumelanins. If it's brown, it's a pheomelanin. And it makes your eyes blue. Okay, hands up. How many people in the room have blue or green eyes? I don't, so I'm going to put my hand down. Okay, you have the same chemical as the rest of us. It's a eumelanin, but your concentration is so low, the little black or brown particles, that you're getting Rayleigh scattering. So eyes are blue for the same reason that the sky is blue. And your eyes are green because they're halfway between blue and brown, and you get a green when you mix those. So that's kind of cute. This is a funny substance, eumelanin. It turns up not only in things like cancer protection in the human body, but it turns up in neural processing in mammals. For example, albino cats are deaf. There you go. It's linked to the melanin. No one's quite sure how, but it's linked to the melanin. This is the only naturally occurring semiconductor. It's photostable. It's been evolved by nature to just last. It doesn't degrade. At room temperature and pressure, it's an amorphous semiconductor, which is not useful. But when you take it into a vacuum and cool it down, it's got the same insulating properties as wood. over a broad range of wavelengths. I think this was 350 to 800 nanometers. Let's check. Didn't show. 99.94% of hundreds of nanometers of light gets turned into phonons. So it's very efficient at turning light into phonons. It has no spectral features. That's really odd for a complicated organic molecule. There should normally be lumps and bumps. But this thing has evolved to have just these monotonic curves. And it's very, very black. This is the Beer's law coefficient, and you can't read that, but that says 5 by 10 to the 6. Sorry, 5 by 10 to the 5, 500,000. And from, say, 350 out to the band gap at 730, it's just constantly black. Then it gets a little bit brown, but it's still only dropping to 100,000, even by over 1,000 nanometers. So it's very black. We can make stable films of it. Oops. Yeah. So that's one way that we're trying to build better photon counters. I'm going to stop there, I think. Let's have a break, and we'll come back. We'll talk about how you can encode information in different quantum systems to what we've discussed so far. Thank you.
Questions?
Even with the two-level system of hydrogen that is not going to exactly give you the ground state, you need more. You need at least perhaps a second state as well, right?
So the question's about the molecular hydrogen model we did.
Yeah.
So with that, we simulated the ground and first three excited states. And how you do that is you change the, it's a control qubit going in, there's some unitary here, and there's a registry of qubits here. And then you throw these qubits away, and you measure out 1 bit at a time the phase that this qubit picked up from its interaction with the circuit. By changing the eigenstate that's encoded into that register, you can change whether you're looking at the ground, first, second, third exciting states.
Any other question? So I will try to come back in 5 minutes for us.
Oh, give them 10. Coffee.